Hello, my name is Joshua Taylor, and this is my lab report for Lab 5, Faraday's Law. Here's the table of contents. The purpose of this lab is to observe and simulate a magnet falling through a conductive tube of aluminum foil, and we'll compare and interpret the results. The models used to do so are both physical with a bar magnet and roll of aluminum foil, and computational with a simulation on GlowScript. The experimental fall time was 1.172 seconds, while the computational fall time was 1.045 seconds. A regular fall time with no tube would be 0.3 seconds. For the relevant equations and principles, on the left, we'll have Newton's second law, stating that the net force on a system is equal to its change in momentum over change in time. We also have some relevant kinematics equations using net force. That's the velocity update formula and the position update formula. Then on the right, we have the Biot-Savart law, which describes the magnetic field produced by a bar magnet. And then below we have equations relating to Faraday's law, stating that the change in magnetic flux can be turned into an induced current and an induced force against the object creating the magnetic field. So we have a physical and computational model used in this experiment. In these experiments, the system is the bar magnet and the surroundings are the aluminum foil tube, the earth, and everything else. For the experiment, a nearly full roll of aluminum foil's dimensions were measured using a meter stick, and these dimensions will be used later in the coding portion of the lab. The tube was held vertically in the air, and a bar magnet was dropped through the center of the tube. This process was repeated 5 times, and a phone videoing each trial was used to determine the time it took for the bar magnet to fall from one end of the tube to the other. We assume that the falling magnet does not contact the walls of the tube. So the results, we have an average fall time of 1.172 seconds. If there was no tube, that fall time would be about 0.3 seconds. Here are the dimensions of the tube that we'll use for the initial conditions of the code later. And just a note, a ferrous tube, which is one made of iron, would produce its own magnetic field and interfere with the falling magnet's magnetic field. So that's why we don't use a ferrous tube and we use the aluminum foil tube. For the coding portion of the lab, we'll hop over to GlowScript. See, we have some constants at the beginning, initial conditions for the geometry of the tube. We have the mass of the magnet and the magnetic moment of the magnet calculated in Lab 3. We have the code for the Biot-Savart law, the magnetic field of the magnet. And then we calculate the change in flux with this code right here. We see how that change in flux creates an induced current which opposes the falling magnet using its own magnetic field. And then we use those two forces of gravity pushing the magnet down and magnetic force pushing it up. We put them together and use those to change the position and velocity of the bar magnet as it falls. Running this program, we will see these red and blue rings that fall with the magnet, and we have a graph generated of the velocity of the magnet versus time. Before we interpret the results, let's go through some possible sources of error. In the code, we assume there is no air resistance and that the magnet does not hit the walls of the tube. These assumptions speed up the fall time. And then we had digital limitations in the calculation of the experimental fall time as we scrubbed through the video of the magnet falling and see when it enters and leaves the tube. So the blue ring around the tube as the magnet falls represents clockwise current, while the red represents counterclockwise induced current. We know this because Lenz's law states that the current generates in an effort to oppose the change in magnetic field as the magnet falls through the tube. If you flip the magnet around, the blue and red would also flip. The total time in the tube for the computational model was 1.045 seconds, which is slightly faster than in real life because of the assumptions made earlier. Accounting for such assumptions would make the model more accurate. And then if we look at the graph, we see that in the beginning, the force of gravity is prevalent and the velocity increases in the negative y direction. And then the forces of gravity and magnetic forces opposing the falling magnet equal out as the magnet is falling through the center of the tube before falling out the other side and gravity takes back over. So for the what if question, a lower resistance means an increased induced current, and this current would exert a greater force against the magnet, making it fall even slower. And for the second what if question, a full ring is necessary for induced current, so any ring with a hole or slot in part of it would not contribute to the opposing magnetic force, and the magnet would fall faster. In conclusion, Faraday's law can be displayed and proven in this experiment as a bar magnet seemingly defies gravity on its way down a conducting tube. And if you want the fall time to occur slower, you reduce the resistivity. If you want it to go faster, you reduce the number of full rings around the tube. Thank you.